Look up at the night sky for a moment. What do you see? A peaceful, twinkling tapestry of distant stars, maybe a planet or two, the serene glow of the moon. It's a view that's instilled wonder for millennia. But what if I told you that this cosmic calm is an illusion, that behind the serene darkness, the universe hides truths so strange, so unsettling, that they challenge everything we think we know about reality itself? We gaze upward searching for answers, but sometimes the universe gazes back with mysteries we aren't prepared to face. Today, we're pulling back that curtain of stars to explore the 30 most terrifying space theories that scientists are grappling with right now. These aren't science fiction fantasies or wild conspiracy theories. These are serious, evidence-based ideas that push the boundaries of physics, philosophy, and human comprehension. From concepts that question the very nature of our existence to forces so powerful and bizarre they defy imagination, this journey isn't for the faint of heart. We're venturing into a realm where black holes might not be what they seem, where entire dimensions could exist just beyond our perception, and where the fate of the cosmos hangs in a balance more delicate and terrifying than we ever dreamed. This is more than a countdown, it's an expedition into the profound unknown, a confrontation with possibilities that stir both awe and unease. So find a comfortable seat, maybe leave a light on, and prepare to see the universe in a completely new and startling way. Because once you learn these theories, the night sky will never look the same again. And so we begin with a theory that hits remarkably close to home, a concept that might just explain the eerie silence of the cosmos and serve as a stark warning for our own future. This is the idea of the Great Filter, a potential solution to the famous Fermi paradox. The paradox, named for physicist Enrico Fermi, poses a simple but haunting question. If the universe is so vast and so old, with billions of planets that could support life, then where is everybody? Why have we seen no signs, no signals, no visitors from any other civilization? The Great Filter proposes a terrifying answer. There is some kind of monumental barrier, a cosmic checkpoint that prevents life from progressing to the point of becoming a visible interstellar species. This isn't just a single event, but a series of incredibly difficult steps, any one of which could act as a filter that wipes out a civilization or prevents it from ever emerging in the first place. Think about the immense challenges life must overcome. First, you need the right conditions for the right organic molecules to form on a planet within its star's habitable zone. Then, those molecules must somehow self-organize into the first self-replicating life, a leap we still don't fully understand. Let's assume a civilization beats those odds. They then have to evolve intelligence, develop technology, and navigate their own potential self-destruction without turning their advancements into instruments of their own doom. The frightening implication of the Great Filter is that we, humanity, might not be special or early. We might simply be next in line. The filter might still be ahead of us, waiting. This is where the theory moves from abstract cosmic speculation to a deeply personal cautionary tale. What could this filter look like for us? Many scientists point to the very technologies that define our modern era. The development of nuclear weapons created a potential filter for the first time in the 1940s, a means by which a global war could irreversibly set back or even obliterate our civilization in a single afternoon. Today, we face other candidate filters, runaway artificial intelligence that we might not be able to control, engineered pandemics released either by accident or design, or the slow boil catastrophe of climate change altering our planet's ability to support a technological society. Each of these represents a challenge so profound that failing it could mean joining the silent, countless civilizations that the universe has already filtered out. The most unsettling part of this entire idea is that we have no way of knowing if we've already passed the Great Filter or if it still lies in our future. If the filter is behind us, say, the improbable jump from non-living chemistry to the first life, then perhaps our future is open and expansive among the stars. But if the filter is ahead of us, then every technological step forward brings us closer to our own potential oblivion. The silence of the universe suggests that the filter is brutally effective, and that very silence is what makes the Great Filter one of the most chilling theories in all of astronomy. It forces us to look at our own world, our own choices, and wonder if we are wisely navigating our path or blindly marching toward a cliff that has ended countless civilizations before our own. If the Great Filter leaves you contemplating the silence, the dark forest hypothesis offers a far more active and menacing explanation for it. This theory imagines the cosmos not as a lonely, empty place, but as a place teeming with life that is deliberately and terrifyingly hidden. Picture an ancient pitch-black forest in the dead of night. You are a hunter lost in those woods. You hear a twig snap. You see a shadow move. Is it a friend? A harmless animal, or another hunter, cold, paranoid, and heavily armed? In that situation, the safest, most rational assumption is that every other sound, every other shape is a lethal threat. To reveal your own position is to invite an attack, so you stay absolutely silent, you listen intently, and you are prepared to shoot first at the slightest sign of another presence. Now scale that scenario up to a galactic level. In the dark forest model of the universe, every star system could be a hunter hiding in the trees, and every civilization is faced with the same brutal logic. The foundation of this idea rests on a few grim but seemingly reasonable axioms. First, every civilization's primary goal is survival above all else. Second, civilizations will always seek to expand and acquire more resources to ensure that survival, meaning eventual conflict over finite galactic real estate, is almost inevitable. And third, there is an unimaginable gap in technology between a young species like ours and any civilization that has already mastered interstellar travel. From our perspective, they would be like gods possessing power we can't even comprehend. This creates a situation of ultimate cosmic paranoia. An advanced civilization can never be certain of a newcomer's intentions. Given the potential for a younger species to experience a rapid technological explosion and become a threat in the future, the most logical and cost-effective strategy is preemptive and total annihilation. It's not necessarily born of malice, but of cold, pragmatic calculation. Why risk your billion-year-old civilization on the hope that the new kids on the block are friendly? This hypothesis provides a devastatingly simple answer to why we haven't heard anyone. Broadcasting your location is suicide. Initiatives like SETI, which listens for signals, might be safe, but actively transmitting messages into the void, something we have already done with powerful radio broadcasts and targeted signals like the Arecibo message, could be the equivalent of standing in that dark forest and screaming, "I'm over here." This theory suggests that truly advanced societies aren't just quiet. They are masters of stealth and concealment, carefully pruning any emerging civilization that makes too much noise before it can become a problem. The eerie silence of space is not a sign of emptiness, but the result of a universe-wide game of hide and seek where being found means extinction. It implies a cosmos where the first law of astronomy is not to explore, but to survive, and where the only civilizations that last are the ones who learn to be utterly silent and ruthlessly vigilant. But if the idea of a silent, predatory universe makes you feel small, our next theory threatens the very foundation of your own reality. We take for granted that our consciousness, our memories, and our experiences are genuine, but what if they are nothing more than a fleeting cosmic accident? This is the profoundly unsettling paradox of the Boltzmann brain. The concept is named for the 19th century physicist Ludwig Boltzmann, who helped pioneer the field of statistical mechanics. His work dealt with entropy, the natural tendency of the universe to move from order to disorder. But within this framework lies a bizarre and terrifying implication. Given enough time, the random motion of particles in a vast, empty universe could theoretically, by pure chance, assemble a fully formed conscious brain. Not an evolved brain in a body, but a lone, disembodied brain that spontaneously congeals from the chaos of the vacuum, complete with a full set of intricate but entirely false memories, senses, and a complete illusion of a life it never lived. To understand why this isn't just science fiction, we have to look at the ultimate fate of the cosmos. Many cosmological models point toward a heat death, a far future state where the universe has expanded so much that it becomes an incredibly vast, cold, and nearly empty void. In this state, entropy is at its maximum. Everything is in a state of total disorder. But quantum mechanics tells us that even in this empty void, particles are constantly flickering in and out of existence. And given an almost unimaginable amount of time, trillions upon trillions of years, these random fluctuations could produce anything, no matter how complex. It is statistically more likely for a single, fully formed brain to randomly assemble than it is for an entire universe with galaxies and stars and planets to form. So, if the universe truly persists in a high entropy state for eternity, the number of these random Boltzmann brains should vastly outnumber the ordinary brains that evolved in an ordered, low-entropy universe like our own. This leads to a devastating statistical conclusion. If Boltzmann brains are more common, then you are statistically far more likely to be one of these random fluctuations. A momentary spark of consciousness with fabricated memories of reading this script, of having a childhood, of believing you are a real person in a real world, then you are to be a genuine product of billions of years of evolution. Your entire reality, everything you think you know and have experienced, could be nothing more than an elaborate and utterly convincing illusion that will dissolve back into the chaotic void in the next instant. Philosophers and physicists grapple with this because it represents an ultimate crisis of epistemology, the study of how we know what we know. If our most fundamental tool for understanding the universe, our own reasoning, could be the product of random chance, then we can never truly trust any observation or conclusion we make. The theory is so troubling that many scientists see it not as a reality, but as a reductio ad absurdum, a sign that our current understanding of cosmology, particularly the ultimate fate of the universe, must be flawed or incomplete. The fact that we observe a universe with such a low state of entropy, a universe that clearly had a beginning and has not yet reached that eternal equilibrium, is our best evidence that we are not Boltzmann brains. But the idea persists as one of the most existentially frightening in all of physics, because it uses the laws of nature themselves to undermine the very reality those laws describe. It suggests that at the most fundamental level, the cosmos might be not just strange, but fundamentally irrational, capable of conjuring phantom minds that question their own existence in a void that has no answers. But if the concept of a randomly generated consciousness makes you question your own existence, our next theory threatens to erase existence itself, not with a bang or a whimper, but with a silent, undetectable click of a cosmic off switch. We think of the vacuum of space as just empty nothingness, a void, but modern physics tells us that this void is not truly empty. It's a seething, bubbling quantum foam full of temporary particles and fields. And crucially, these fields exist in a state known as a false vacuum. Think of it like a ball resting in a small dip on the side of a much, much larger valley. The ball is stable for now, but it's not in the lowest possible energy state. It's in a metaphoric valley of false stability. The true lowest energy state, the true vacuum, is that much deeper valley below. All it would take is a tiny nudge for that ball to roll out of its shallow dip and plummet downward, releasing a catastrophic amount of energy in the process. Now imagine that ball is the entire quantum field that underpins our universe, and the shallow dip it rests in is the state that allows for the existence of atoms, forces, and life as we know it. The terrifying possibility of vacuum decay is that somewhere in the universe a quantum fluctuation could provide that tiny nudge. This wouldn't be an explosion in the conventional sense. It would be a fundamental phase change in the fabric of reality. A microscopic bubble of true vacuum could spontaneously form. The laws of physics inside this bubble would be completely different from our own. The constants we rely on, like the speed of light or the strength of gravity, could be altered, making the formation of any kind of matter or chemistry as we understand it utterly impossible. This bubble would then expand in all directions at the speed of light, rewriting the universe as it goes. The wall of this expanding sphere would be a wave of total annihilation, not of destruction but of erasure. There would be no force that could stop it, and because it moves at the universal speed limit, there would be no warning. One moment, the universe is there. The next, it's gone, replaced by something incomprehensible and barren. What makes vacuum decay so uniquely horrifying is its combination of inevitability, speed, and utter totality. If this process is possible, it's not a matter of if but when, and it could be triggered at any moment in any location by a random quantum event. A region of space 1 billion light-years away could have already undergone this decay, and the sphere of true vacuum could be on its way to us right now. We wouldn't know until it arrived, because the first sign of its approach would be the instantaneous dissolution of our local physical laws. There would be no time to react, no hope of escape, and no one left to even comprehend what had happened. The entire cosmos, with all its galaxies, stars, planets, and history, would simply cease to be in the way we understand it, overwritten by a new, sterile set of rules. It represents an ultimate and absolute end, not just to life, but to the very framework that allows anything to exist at all. Yet for all its terrifying power, the Big Rip is a slow and distant apocalypse unfolding over billions of years. But what if the end could come not from the expansion of space itself, but from the heart of a failed experiment, one that could unravel the very fabric of the cosmos in a fraction of a second? This brings us to one of the most controversial and spine-chilling theories in modern physics, the idea that our universe is not the first, and that a previous civilization's high-energy experiments might have already triggered a cataclysm that we could be on the verge of repeating. This brings us to a theory that shifts the terrifying nature of the cosmos from external forces to the very nature of our own perception. What if the universe's most bizarre qualities aren't bugs but features? What if the reason quantum particles behave so strangely, only resolving into a definite state when we observe them, is because the simulation is optimizing processing power, only rendering the fine details when someone is looking? This line of thinking is the core of the simulation hypothesis, the idea that our entire reality, from the farthest galaxy to the feeling of your chair beneath you, is not base reality, but an incredibly advanced digital construct, a universe-sized video game run on some unfathomable computer. It's a concept that has moved from the fringes of philosophy to a subject of serious debate among technologists and physicists, and the evidence they point to is far more compelling than you might think. Consider the world around you not as a thing but as a set of rules. The laws of physics are remarkably mathematical. They aren't just described by math, they are math. Energy, momentum, and charge are quantized, meaning they exist in discrete, countable packets, much like the pixels on a screen or the bits in a computer. The universe appears to run on a code. Even the speed of light, that ultimate universal speed limit, can be seen not as a physical barrier, but as a processing limit, the maximum clock speed of the cosmic CPU, preventing the simulation from having to process infinitely complex interactions. Why does the quantum world remain a blurry cloud of probabilities until it is measured? A resource-conscious simulation wouldn't waste cycles calculating the precise position and momentum of every subatomic particle in a distant, empty void. It would only resolve those details when the system demands it, when an observation is made. This isn't just efficiency, It's exactly how modern video game engines work, using a technique called procedural generation to create vast, detailed worlds without having to store every single leaf and rock in memory at once. The implications of this being true are, to put it mildly, world-shattering. It means our entire history, our struggles, our loves, and our discoveries could be nothing more than a narrative written for entertainment, for research, or for some purpose we cannot even conceive. Are we the players, or are we the non-player characters? The search for extraterrestrial intelligence takes on a new dimension. Perhaps the reason we haven't found anyone is that we are in a simulated historical preserve, a recreation of an early universe designed to study how civilizations develop in isolation. Every unexplained glitch, every strange coincidence, every déjà vu moment takes on a potential new meaning. But the most profound terror of the simulation hypothesis is not that we might be in a simulation, but the existential question it raises about reality itself. If a future civilization can create a perfect simulation containing conscious beings, then statistically, it is almost certain that there would be billions of simulated universes for every one base reality. Therefore, the odds are overwhelming that we are not in the original reality, but in one of the countless simulations. Our entire existence, our very consciousness, could be a fleeting data stream in a vast cosmic computer, destined to be shut off when the experiment ends or the user gets bored. It's a theory that doesn't just threaten our place in the universe, but the very authenticity of our being. After confronting the possibility that our reality might be a sophisticated simulation, we arrive at a theory that is perhaps less existentially dizzying, but no less unsettling in its implications for our place in the cosmos. This is the zoo hypothesis, a potential solution to the Fermi paradox that paints a picture of Earth not as an insignificant rock, but as a meticulously curated exhibit in a vast interstellar nature preserve. Imagine if a tribe of uncontacted people deep in the Amazon were to look up at the sky and see a silent, high-altitude drone observing them. They would have no way of understanding its purpose, its origin, or the civilization that sent it. From their perspective, the sky is empty, yet they are being watched. The zoo hypothesis suggests that this is our precise situation on a galactic scale. The core premise is that a community of advanced extraterrestrial civilizations exists, and they have collectively agreed to a policy of non-interference with developing worlds like our own. Their reasoning could be rooted in a kind of cosmic prime directive, a moral or scientific code that values the natural, uncontaminated evolution of life above all else. To them, we are a fascinating subject of study, a living museum of a primitive technological society, and any contact would irrevocably spoil the experiment. Our cultures, our wars, our art, our slow climb toward understanding the universe, all of it is observed from a respectful distance, recorded and analyzed without ever offering a hint of their presence. This would explain the great silence not as a sign of our solitude or imminent doom, but as a form of enforced quarantine for our own protection, or more accurately, for the purity of their research. This theory forces us to confront profound and uncomfortable questions about human agency and freedom. If true, it means our entire history, every achievement and every failure, has unfolded under the silent, unblinking gaze of observers infinitely our superior. Our belief in our own autonomy, our sense that we are the captains of our own fate, could be a complete illusion. Every rocket we launch might be tracked, every nuclear test monitored, and every radio broadcast collected and filed away in some alien archive, all while the curators ensure we remain confined to our planetary enclosure. The dream of one day venturing out to meet other civilizations among the stars suddenly transforms into a dispiriting prospect. We might find the galaxy already fully mapped, governed, and off-limits, with invisible fences around our solar system that we are not permitted to cross. Yet, the zoo hypothesis also contains a sliver of hope, or at least a reprieve from more terrifying alternatives. It suggests we are not in immediate danger of annihilation from a dark forest. We are not alone, but we are being left alone, which is a far gentler fate than being preemptively eliminated. However, this protective isolation raises a chilling secondary question. What happens when the animals in the zoo become aware of their cage? Our technological progress, particularly our development of radio telescopes and attempts at active SETI, signals that we are on the verge of realizing we are in an exhibit. This awareness could be the very event the curators have been waiting for, the moment a species achieves a certain threshold of cosmic maturity. Perhaps our first real contact will not come from us finding them, but from them finally deciding we are ready for the truth, ending our millennia of innocence and welcoming us, as naive and unprepared as we are, into a galactic community whose rules we have yet to learn. While the zoo hypothesis questions our freedom within the cosmos, our next theory turns that existential gaze inward, toward the most intimate and terrifying frontier of all, the nature of our own consciousness and its relationship with death. This is the mind-bending and deeply personal paradox of quantum immortality. To understand it, we have to venture into the weird world of quantum mechanics, specifically the many worlds interpretation. Unlike the traditional Copenhagen interpretation, where a quantum particle's possibilities collapse into a single reality upon observation, the many worlds theory proposes that every possible outcome of every quantum event actually happens. Each time there is a probability, the universe doesn't choose, it splits. Every possibility branches off into its own separate, equally real timeline, creating a mind-boggling multiverse of infinite variations. Now apply that splitting to your own life. Every moment, countless quantum events are happening in your body and in the world around you. Each one represents a fork in the road. In most of these branches, your life continues normally, but sometimes you encounter a life-threatening situation. Imagine you're in a catastrophic car crash. In the vast majority of the new timelines branching from that event, you die. But according to the logic of quantum immortality, from your first-person perspective, you can never experience the cessation of your own consciousness. You can only experience the timelines in which you are alive. Therefore, your conscious experience will always follow the increasingly narrow and improbable branch where you survive. Maybe a metal beam miraculously twists in just the right way to shield you. Perhaps a paramedic arrives seconds earlier than in any other timeline. Your survival might be astronomically unlikely, but in an infinite multiverse, even the most improbable event must happen somewhere. And your consciousness, from your point of view, is perpetually that somewhere. This leads to a staggering and deeply unsettling conclusion. You might be effectively immortal, not through magic or technology, but through sheer probability. You would never ultimately experience your own death. Instead, you would find yourself repeatedly cheating it, surviving disasters through a series of ever more implausible miracles. A gunshot jams at the last nanosecond. A terminal illness goes into spontaneous, inexplicable remission. You would live on, watching everyone else age and die around you, while you continue to sidestep the Grim Reaper through a perpetual, unconscious luck that defies all odds. Over eons, you could become a solitary, ageless observer on an Earth that changes beyond recognition, forever trapped in a reality that seems to bend over backwards to keep you alive. Yet this immortality is arguably a form of eternal torture, a curse rather than a blessing. The theory suggests that while your consciousness continues, the quality of that existence could deteriorate horrifically. You might survive a nuclear explosion, but your branch of reality could be a charred, radioactive wasteland where you live in immense suffering, only to then survive that too, and the next catastrophe, and the next. You would be a constant prisoner of experience, unable to ever finally rest. The most profound terror of quantum immortality isn't just the potential for endless life, but the nightmarish isolation and the psychological burden of outliving everything and everyone. all while knowing that your continued existence is a statistical fluke in a cosmos that is overwhelmingly indifferent to your survival in almost every other reality. It forces us to ask a haunting question: is death a tragedy, or is it, in fact, a final and necessary mercy? But this unsettling view of personal destiny through a quantum lens leads us directly to a paradox that unravels at the very largest scales of cosmic destruction. If our own consciousness might persist through bizarre probabilistic twists, what happens to the fundamental information that defines everything else in the universe when it meets the most absolute endpoint we know? This brings us to a conflict so deep that it pits the two most successful theories in physics against each other in a battle over the soul of reality itself, the black hole information paradox. At its heart, this is a crisis about what happens to the stuff that makes a thing itself. In our everyday world, if you burn a book, it seems destroyed. But in principle, a physicist with perfect knowledge could collect every bit of smoke, every pile of ash, and trace the heat radiating away to reconstruct the exact arrangement of atoms that made up that book, and even the precise words printed on its pages. The information, the unique identity of the object, is not truly lost. It's just scrambled and dispersed according to the strict, unbreakable rules of quantum mechanics. This is a cornerstone of our understanding of the universe. Information must always be conserved. It can never be truly created or destroyed. Now throw a book into a black hole. According to Einstein's general relativity, the book would cross the event horizon, the point of no return. It would be pulled inexorably toward the singularity at the center, a point of infinite density where the laws of physics as we know them simply break down. From the perspective of the outside universe, that book and all the information it contained is gone forever. It's not just scrambled, it is irretrievably erased from our reality. This presents a monumental problem. Stephen Hawking's groundbreaking work showed that black holes aren't completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles now known as Hawking radiation. But here's the catch: this radiation is purely thermal. It's random noise like the static from an old television. It contains no information whatsoever about what fell into the black hole. When the black hole finally evaporates completely, all it leaves behind is this featureless burst of heat. The information about the book, the star, or the spaceship that fell in is seemingly lost forever, violating the most sacred principle of quantum physics. This leaves physicists with a terrifyingly unsolvable puzzle, often described as losing the keys to the universe. Either general relativity is wrong about what happens at the event horizon, or quantum mechanics is wrong about the conservation of information. We have to choose between breaking our understanding of the very large or the very small. If information can be lost, it means the universe is fundamentally unpredictable and unaccountable. The history of events becomes blurry and ultimately erased, undermining the cause and effect structure that all science is built upon. It would mean that reality itself has a certain fuzziness, a forgetfulness at its core, where things can simply vanish without a trace. The proposed solutions to this paradox are as strange as the problem itself. Some, like the famous holographic principle, suggest that all the information about what falls into a black hole is not lost inside, but is instead smeared across its two-dimensional event horizon like a cosmic fingerprint encoded on the surface of the black hole itself. Others propose that black holes don't evaporate completely but leave behind a tiny, stable remnant of fossil that contains all the compressed information of everything it ever consumed. And there are even more radical ideas, like every black hole giving birth to a new baby universe inside itself, where the information is preserved but completely inaccessible to us. Each solution tries to save the laws of physics, but in doing so, it forces us to accept a universe far weirder and more interconnected than we ever imagined. The information paradox isn't just an academic debate. It's a profound struggle to understand whether the universe ultimately remembers or if it is capable of the most final form of forgetting. Yet this slow-motion cosmic doom might feel abstract, a fate for a universe so far in the future it's almost not our concern. But the false vacuum collapse presents a threat that is both immediate and horrifyingly final. We already explored the concept of vacuum decay, the idea that our universe rests in a fragile, metastable state and could suddenly plummet into a true vacuum, rewriting the laws of physics. But the true terror isn't just that this could happen randomly, it's that we might accidentally be the ones to trigger it. The most chilling scenario involves our own pursuit of knowledge, where a high-energy physics experiment could become the tiny, catastrophic nudge that unravels all of reality. To understand how, we need to look at the tools we use to probe the secrets of the universe, particle accelerators like the Large Hadron Collider. These immense machines slam subatomic particles together at velocities incredibly close to the speed of light, recreating for a split second the kinds of energies and conditions that haven't existed since the Big Bang itself. The goal is noble: to discover new particles, to understand the fundamental forces, to glimpse the very origins of everything. But some theorists have posed a deeply disturbing question. What if, in our quest to create these infinitesimally small, high-energy conditions, we create something we cannot control? The concern is that these ultra-powerful collisions could, in theory, create a microscopic bubble of true vacuum. It would be a speck of space where the laws of physics are different, a seed of a new, alien reality that is fundamentally more stable than our own. And according to the rules of physics, that which is more stable will inevitably expand. This bubble wouldn't grow like an explosion of fire and debris. It would expand at the speed of light, and its edge would be a wave of instant, absolute transformation. The moment it touches any region of space, the Higgs field, the field that gives particles their mass and allows atoms and chemistry to exist, would collapse into its true, lowest energy state. The constants of nature would change instantly. The very glue that holds atoms together would cease to function as it does now. Molecules would disintegrate. Matter itself would simply stop being matter. Life, planets, stars would not be destroyed in a conventional sense. They would be erased, unmade from the inside out, replaced by a new state of existence that is almost certainly incompatible with any form of life as we understand it. And because this wave moves at light speed, there is no warning. One moment the Earth is here, the next nanosecond it is gone, along with our entire galactic neighborhood, all consumed by a sphere of new physics that is expanding across the universe. The most frightening aspect of this scenario is its sheer inevitability once initiated. There is no force known to science that could stop or contain this process. It wouldn't matter if we realized our mistake a picosecond after creating the bubble. The deed would already be done. The entire cosmos, with all its history and potential, would be on a countdown timer set by the speed of light. And while the probability of such an event is considered vanishingly small by most physicists, the LHC has been running for years with no universe-ending incidents. The stakes are so infinitely high that even the smallest non-zero chance is enough to fuel profound existential dread. It represents the ultimate form of Russian roulette, where pulling the trigger is a scientific experiment, and the consequence of failure isn't just our death, but the death of everything, everywhere for all time. Our innocent curiosity to understand the cosmos could, in the most extreme and terrifyingly plausible worst-case scenario, be the very thing that ends it. Just when you thought the cosmos couldn't get any more menacing, we arrive at a theory that suggests our own sun might be hiding a dark and deadly secret, a murderous twin. This is the Nemesis star theory, a hypothesis that proposes our solar system is not a solitary star with its family of planets, but a binary system. And this second star, nicknamed Nemesis, is no benevolent companion. It's a dim, distant, and sinister orbit partner whose regular passage through the outer reaches of our solar system sends a rain of death and destruction toward Earth, triggering catastrophic mass extinctions on a precise apocalyptic schedule. The story of this theory begins not in the stars but in the geological record here on Earth. Paleontologists studying the history of life have identified a grim pattern. Approximately every 26 to 30 million years, life on our planet is dealt a devastating blow. The fossil record shows a significant number of species abruptly vanishing in these events. The most famous is the Cretaceous-Paleogene extinction that wiped out the dinosaurs 66 million years ago, but it's just one of many. For decades, the cause of this eerie clockwork cycle of death was a profound mystery. The sheer regularity pointed to a cause that wasn't random, like a single asteroid impact, but something cyclical, a celestial metronome of doom ticking away in the darkness. Astronomers searching for an explanation looked outward and landed on the Oort cloud, a vast spherical shell of icy planetesimals and comets that surrounds our solar system far beyond the orbit of Pluto. This cloud is the source of long-period comets, those that take thousands or even millions of years to complete a single orbit. The hypothesis is that our Sun has a binary companion, a small, cool red dwarf, or perhaps a failed star known as a brown dwarf, that follows a highly elongated 26 million-year orbit. As this dark star, dubbed Nemesis, swings in on its closest approach to the Sun, its gravity violently perturbs the outer Oort cloud. Like a gravitational cue ball breaking a rack, Nemesis's passage sends a shower of countless icy comets careening inward. Many of these comets are flung out of the solar system entirely, but a significant number are aimed directly at the inner planets, turning Earth into a target in a cosmic shooting gallery. The evidence for this theory is compelling yet circumstantial. The periodicity of extinction events is its strongest pillar. Furthermore, the impact craters on Earth and the Moon also appear to show a similar cyclical pattern, suggesting periods of intense bombardment from space. The logic is brutally simple. More comets coming inward means a statistically higher chance of a planet killer, a several-mile-wide ball of ice and rock slamming into Earth. The aftermath of such an impact is the stuff of nightmares. It would blast a crater dozens of miles wide, sending superheated ejecta raining down across the globe, triggering global firestorms. The immense energy released would vaporize rock and trigger continent-spanning earthquakes and volcanic eruptions, but the real killer would be the long-term environmental collapse. The impact would throw so much dust and soot into the upper atmosphere that it would blot out the sun for years, causing a brutal impact winter. Photosynthesis would halt, food chains would collapse, and ecosystems would unravel, leading to the mass extinctions we see fossilized in stone. The most unsettling part of the Nemesis theory is that this killer could be out there right now, invisible to our telescopes on its long, slow journey back toward us. A dim red dwarf, or especially a cold brown dwarf, would be incredibly difficult to detect at such a great distance. It would be a ghost in the interstellar darkness, its presence inferred only by the carnage it leaves in its wake. While extensive astronomical surveys like NASA's A Wise Mission have largely ruled out the existence of a large star or brown dwarf within a certain range, the possibility of a smaller, fainter object still lingers. The Nemesis star theory forces us to confront a terrifying possibility that our Sun, the source of all life and warmth, might be locked in a deadly gravitational dance with a partner that brings only periodic oblivion. It suggests that the very architecture of our solar system could be programmed with a timer for apocalypse, and that timer may still be counting down. Building directly from the unsettling logic of quantum immortality, we can push this thought experiment to its most extreme and personally horrifying conclusion with a related idea known as quantum suicide. This is not a theory to be tested, but a stark philosophical paradox designed to probe the deepest implications of the many worlds interpretation. imagine a devastatingly simple, though macabre, experiment. A volunteer is seated before a specially designed apparatus, a gun, perhaps, or a vial of poison, that is triggered by the decay of a single radioactive atom. In any given second, the probability that the atom decays and fires the weapon is exactly 50%. According to the rules of quantum mechanics, at the moment the trigger mechanism is activated, the universe splits. In one branch, the atom decays and the weapon fires. In the other, it does not, and the subject lives. Now, imagine this experiment is set to repeat over and over again every second. From the perspective of an outside observer, this is a tragically short experiment. They would see their friend or colleague participate, and within a few seconds or minutes, they would almost certainly see the weapon fire. The observer would witness a death and could verify that the many worlds theory is consistent with a single, sad outcome. But what about from the perspective of the volunteer? If the many worlds interpretation is correct, the volunteer's conscious experience would never include the outcome of their own death. With each trigger pull, their consciousness would only follow the branching path where they survive. They would hear a click each time the weapon fails to fire. After 1 minute, they are alive. After 1 hour, still alive, having miraculously beaten 50-50 odds 60 times in a row, an event so statistically improbable it borders on the impossible. After a day, a week, a year, they would still be sitting there, listening to an endless series of clicks, becoming a living testament to the power of quantum branching. This thought experiment forces a brutal distinction between reality as witnessed by a third party and reality as experienced from a first-person point of view. To the outside world, the volunteer is dead in the overwhelming majority of branches. But from the volunteer's own subjective viewpoint, they are not just alive, they are effectively immortal within the confines of this experiment. They would possess what seems like God-like luck, a perpetual escape from death that would, over time, feel less like luck and more like an unbreakable law of their personal reality. This creates a terrifying form of solipsism, where one's own consciousness seems to warp probability itself, ensuring its own continued existence no matter the odds. The profound and deeply disturbing implication of quantum suicide is that it could be used as a potential test for the many worlds interpretation. If someone were actually reckless enough to conduct this experiment and found themselves surviving against all probability, it would be powerful evidence that they are indeed sliding through a multiverse, their consciousness perpetually hitchhiking on the narrow branch of reality that allows it to continue. Of course, no one would ever be able to report the results, because in every branch where they try, they die and cannot communicate, and in the branch where they survive, they have only their own unbelievable experience as proof. This leaves the volunteer in a state of ultimate isolation, a prisoner of their own consciousness in a universe that seems to conspire to keep them alive, yet forever unable to convince anyone else of their bizarre and lonely truth. It suggests that from a subjective standpoint, death might be an experience that is fundamentally inaccessible to the self, a destination that your consciousness can never actually reach. Just when we thought reality couldn't get any stranger, we arrive at a concept that threatens to dismantle our most basic sensory experience of the world. We live in a three-dimensional universe, or at least that's what our eyes and hands tell us. Objects have height, width, and depth. We move through space in 3 dimensions. But what if this rich, tangible reality is nothing more than an elaborate illusion, a cosmic mirage projected from a flat, 2-dimensional surface at the very edge of the universe? This isn't science fiction. It's a serious and deeply unsettling scientific idea known as the holographic principle. The seeds of this theory were first planted not in the vastness of space, but in the study of the most mysterious objects in the cosmos, black holes. As we discussed with the information paradox, physicists were deeply troubled by the idea that information could vanish into a black hole, seemingly erased from existence. The work of Jacob Bekenstein and Stephen Hawking in the 1970s revealed something astonishing about black holes: the maximum amount of information or entropy a black hole can contain is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it's proportional to the surface area of its event horizon. Think about that for a moment. All the information needed to describe every single thing that ever fell into a black hole, every atom, every person, every planet, could be entirely encoded on the two-dimensional boundary that surrounds it. The three-dimensional interior is, in a sense, redundant. The surface holds the blueprint. This revelation led physicists like Gerard T. Hooft and Leonard Susskind to propose a truly radical idea. If this is true for a black hole, could it be true for the entire universe? Could our entire cosmic existence, with its galaxies, stars, and ourselves, be a holographic projection from a two-dimensional surface at the furthest limits of everything we can see? In this model, the universe we experience is like an incredibly sophisticated and immersive 3D movie, but the film itself, the source code, is stored on a flat, two-dimensional screen surrounding us. Every event, every particle, every force we perceive in 3D space is actually translated from information encoded on this distant, flat surface. The implications of this are enough to make your head spin. It suggests that the fundamental building blocks of reality are not tiny, vibrating strings or point-like particles, but bits of information like the ones and zeros in a computer. The universe is essentially a cosmic data processing system, and the physics we observe are the result of this information being processed and projected. This could even provide a potential solution to the long-sought-after goal of physics, a theory of everything. The holographic principle beautifully unites the laws of gravity, which govern the very large, with the laws of quantum mechanics, which govern the very small, by showing how gravity in our three-dimensional world emerges from quantum processes on the two-dimensional boundary. But the personal, existential terror of this theory is profound. It means that your entire life, every sensation, every emotion, the feeling of the wind on your skin, the depth you perceive when you look at a mountain range, is a magnificent illusion. You are not a solid, three-dimensional being moving through a solid, three-dimensional world. You are a projection, a phantom in a cosmic shadow play. The very dimensionality of your existence is a kind of trick. The universe is, in its most fundamental nature, simpler and flatter than we could ever perceive, and our rich sensory experience is a kind of evolutionary adaptation, a user interface that allows us to navigate a reality that is far more abstract and alien than we ever imagined. We are not just in the universe, we are an image of it, a hologram gazing in wonder at itself. But if black holes represent the universe's ultimate one-way street into oblivion, what lies on the other side of the cosmic road? Enter one of the most speculative and mind-bending concepts in all of theoretical physics, the white hole. As the name suggests, a white hole is theorized to be the exact opposite of a black hole. Where a black hole's event horizon is a point of no exit from which nothing can escape, a white hole's horizon would be a point of no entry, violently expelling matter and energy while refusing to let anything from the outside universe come in. Think of it as a cosmic fountain, endlessly gushing material into space, or a replay button on the universe's most violent event playing in reverse. It's a concept that emerges naturally from the mathematics of general relativity, which is famously time-symmetric, meaning its equations work just as well if you run time backwards. If a black hole is a region of space where matter collapses inward forever, then reversing the time direction gives you a region where matter explodes outward from a singularity for all eternity. The most compelling and grand-scale application of this idea is the possibility that our entire universe began as a white hole. The Big Bang, the moment of incomprehensible density and energy from which everything emerged, shares striking similarities with a white hole event. It was a singular point from which all matter and energy erupted, creating the expanding cosmos we inhabit today. In this view, our universe isn't expanding into some pre-existing void. It is the ongoing eruption from a white hole singularity that occurred some 13.8 billion years ago. This provides a potentially elegant, though still unproven, answer to the question of what came before the Big Bang. Perhaps our cosmos was born from the interior of a black hole in another parent universe. In that scenario, the gravitational collapse of a massive star in another reality formed a black hole, and the singularity at its heart became the white hole Big Bang that birthed our own cosmic reality. We may not be living in a single universe, but in one of countless bubbles in a vast multiverse, each born from the death throes of a giant star in a higher dimensional reality. However, the white hole theory comes with immense, perhaps insurmountable, problems from a physics perspective. The second law of thermodynamics, which states that entropy, or disorder, always increases, seems to be fundamentally violated by a white hole. A black hole is a high-entropy object. It represents the ultimate state of disorder for the matter that falls into it. A white hole, by spewing out ordered, low-entropy material, would appear to be decreasing entropy, effectively making time run backwards in a way that contradicts everything we observe about how the universe works. Furthermore, white holes are considered to be profoundly unstable. Any speck of dust or photon of light attempting to fall into one would add a tiny amount of mass energy, which theoretical models suggest could cause the white hole to instantly collapse and transform into a black hole. This inherent instability is the primary reason most physicists believe that while white holes are beautiful mathematical curiosities, they simply cannot exist in the real, stable universe we observe. Yet, the allure of the idea persists, especially when we look out into the cosmos for evidence. Some astronomers have proposed that incredibly violent and energetic events, like certain types of gamma-ray bursts or the mysterious fast radio bursts whose origins remain unknown, could be potential signatures of a white hole's brief, glorious existence. If a white hole did form, it would likely be a spectacular but fleeting event, a cosmic fireworks show of unimaginable power that flashes into existence and then, just as quickly, collapses into a more stable black hole. While the search for a genuine white hole remains fruitless, the theory continues to captivate because it offers a glimpse into the profound symmetries woven into the fabric of spacetime itself, suggesting that for every terrifyingly dark ending in the cosmos, there might just be a brilliantly luminous beginning. But if the holographic principle suggests our reality is a projected illusion, where does that leave the one thing that feels most undeniably real, our own consciousness? This brings us to one of the most controversial and profound theories at the intersection of neuroscience and quantum physics, the idea of quantum consciousness. The conventional, mainstream view in neuroscience is that the brain is a complex biological computer. Consciousness, in this model, is an emergent property of the electrochemical interactions between billions of neurons. It's a classical system operating according to well-understood laws of chemistry and physics. But this view runs into a formidable obstacle known as the hard problem of consciousness, articulated by philosopher David Chalmers. Even if we perfectly map every neural connection and understand every signal, we still haven't explained how and why these physical processes give rise to subjective experience, the feeling of warmth from the sun, the taste of chocolate, the profound depth of a memory. How does mere matter generate the inner world of the mind? This gap in our understanding has led some scientists to propose a radical alternative. Perhaps the brain isn't a classical computer after all. Perhaps it's a quantum computer. The most famous proponent of this idea was the renowned physicist Roger Penrose, who teamed up with anesthesiologist Stuart Hameroff to propose a specific mechanism. Their theory, called orchestrated objective reduction, suggests that the seat of consciousness lies deep within the neurons, in structures called microtubules. These tiny protein scaffolds are part of the cell's internal skeleton. Penrose and Hameroff propose that these microtubules are small enough to be governed by the bizarre rules of the quantum world. Within them, quantum processes could occur, things like superposition, where a particle exists in multiple states at once, and entanglement, where particles become inextricably linked across distance. In their model, these quantum states within the microtubules persist and interact, forming a complex quantum network throughout the brain. Consciousness arises at the moment these quantum superpositions collapse into a single, definite state. This isn't a random event, but an objective process linked to the fundamental geometry of spacetime itself. This theory is breathtaking in its ambition because it doesn't just place consciousness in the brain, it places it at the very foundation of reality. If true, it means our minds are not mere bystanders in a classical universe. They are active participants deeply woven into the quantum fabric of the cosmos. Our thoughts, our awareness, could be a manifestation of the universe becoming aware of itself through us. The implications of this idea are staggering. It could provide a scientific basis for phenomena that have long been relegated to philosophy and spirituality, such as free will and the unified nature of subjective experience. It suggests that the separation between the self and the universe might be an illusion, and that at the most fundamental level, all consciousness is interconnected through quantum entanglement. This isn't just a theory about the brain, it's a theory about everything, proposing that consciousness is a fundamental force of nature, as basic as gravity or electromagnetism. However, it is crucial to note that the quantum consciousness theory is fiercely contested. The mainstream scientific community raises a powerful objection. The brain is simply too warm, too wet, and too noisy for delicate quantum states to survive for long enough to have any meaningful effect. Quantum coherence, the fragile state required for these processes, is notoriously easily disrupted, a phenomenon called decoherence. We can only maintain it in sophisticated labs under near absolute zero temperatures and perfect vacuum conditions. The chaotic environment of the living brain seems like the last place such delicate processes could thrive. Despite these formidable challenges, the search for evidence continues, driven by the powerful allure of a theory that could finally bridge the chasm between the objective world of physics and the subjective world of experience. Whether it ultimately proves true or not, quantum consciousness forces us to confront the possibility that the universe is not just stranger than we imagine, but that our own inner world might be its strangest and most intimate dimension. But if the violent birth of a white hole offers one potential origin story, our next theory presents a far more ancient and cyclical vision of cosmic fate, one where the universe knows no true beginning and no final end, only an endless, rhythmic cycle of death and rebirth. This is the Big Bounce, a model that replaces the singular, explosive genesis of the Big Bang with a timeless, eternal pulse. In this breathtaking view, our universe is not the first and only one, but merely the latest incarnation in an infinite series, a cosmic phoenix that repeatedly rises from the ashes of its own collapse. The driving force behind this grand cycle is the same mysterious energy we encountered with the Big Rip, dark energy. In the standard model of cosmology, dark energy's repulsive force seems destined to win forever, accelerating the expansion of the universe until it reaches a cold, dark, and dilute state known as heat death. The Big Bounce theory, however, proposes a different, more dramatic finale. It suggests that dark energy might not be constant. Instead, its influence could weaken over time, eventually allowing the attractive force of gravity to reassert its dominance. After trillions of years of expansion, the universe would gradually slow its flight, stop, and then begin the long, slow process of contraction. Every galaxy, every star, every particle would start falling back toward a common center. This great crunch would be the mirror image of the Big Bang, a reverse of cosmic time. As the universe collapses, temperatures and densities would skyrocket. Galaxies would merge in violent embraces, stars would be torn apart, and eventually all matter and energy would be compressed into an unimaginably hot, dense state, a singularity. But here's where the bounce happens. Instead of this singularity representing a final end point where physics breaks down forever, proponents of this theory believe quantum gravity effects would take over. At this extreme, the repulsive force of quantum gravity would become overwhelmingly powerful, acting like a cosmic trampoline. It would halt the collapse and trigger a rebound, a new Big Bang that spews forth a fresh, new universe from the remnants of the old one. The implications of this are as profound as they are terrifying. It suggests that everything we see, every constellation, every planet, every living being, has existed in some form an infinite number of times before, and will do so again an infinite number of times in the future. The universe is caught in an inescapable loop. Your consciousness, your memories, your very existence might not be a unique event, but a scene on a reel of cosmic film that is played, rewound, and played again for eternity. This introduces a haunting form of immortality, but one devoid of any progress or ultimate meaning. Each new cycle might start with slightly different initial conditions, leading to a universe that is similar but not identical to the last. Or it might be an exact repetition, a perfect recurrence where every atom, every thought, every moment plays out in precisely the same way forever. This idea, known as eternal recurrence, forces us to ask a deeply philosophical question. If you were destined to live this exact same life, with all its joy and all its pain, again and again for all time, would you see it as a blessing or the most exquisite form of torture? The Big Bounce offers a universe of endless second chances, but at the potential cost of being trapped in a cycle from which there is no escape and no final resolution. This brings us to a theory that shifts the terror from the abstract and cosmic to something that might have already passed through our own celestial neighborhood. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something unprecedented, a visitor from another star system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. This was the first interstellar object ever detected within our solar system, and from the very beginning it defied all expectations. It wasn't a typical comet or asteroid. Its trajectory was strange, its shape was bizarre, and its behavior sparked a controversy that continues to this day, leading some respected scientists to entertain a possibility once confined to science fiction, that Oumuamua was not a natural object at all, but a piece of alien technology, a probe sent to reconnoiter our corner of the galaxy. Let's examine the anomalous evidence that fueled this extraordinary hypothesis. First, there was its shape. Based on the way its brightness changed dramatically as it tumbled through space, astronomers deduced that Oumuamua was highly elongated, perhaps 10 times longer than it was wide. Imagine a cigar or a pancake tumbling end over end. While there are some elongated asteroids in our own solar system, nothing of this extreme proportion has ever been observed. Then there was its motion. As it traveled away from the Sun, it exhibited a small but significant non-gravitational acceleration. In simple terms, it was speeding up in a way that couldn't be explained by the gravity of the Sun or planets alone. For a comet, this is common. Heat from the Sun vaporizes ice on its surface, creating jets of gas that act like a natural thruster. But Oumuamua showed no visible coma, no cloud of gas and dust around it. It was as dark and inert as a rock, yet it was accelerating as if it had an engine. It was this combination of mysteries that led Harvard astronomer Avi Loeb to propose a radical explanation. What if the acceleration wasn't from comet-like outgassing, but from radiation pressure from the Sun itself? For a natural object, this force is negligible. But for an object that is extremely thin and lightweight, a solar sail, it becomes a viable means of propulsion. A solar sail is a theorized form of spacecraft propulsion that uses the tiny push of photons from a star to accelerate a large, ultra-thin, reflective sheet to tremendous speeds over time. Loeb suggested that Oumuamua's unusual acceleration and its lack of a visible coma could be explained if it were, in fact, a defunct light sail, a piece of alien technology drifting through the interstellar void, and we just happened to catch a glimpse as it passed by. The scientific community, as one might expect, reacted with intense skepticism. The majority of astronomers maintain that while Oumuamua is weird, extraordinary claims require extraordinary evidence, and that it is far more likely to be a natural object with unusual properties we simply don't yet understand. They propose alternatives. Perhaps it was a shard of a planet shattered by a cosmic collision, which would explain its strange shape. Perhaps it was a dusty iceberg made of solid hydrogen or nitrogen, which could have vaporized to provide the thrust without creating a visible dust cloud. The point, they argue, is that we had such a brief window to observe this object, it was already on its way out of the solar system when we spotted it, that we simply lack the data to make a definitive conclusion. To jump to aliens, they caution, is a last resort, not a first principle. However, the alien probe hypothesis forces a crucial and unsettling shift in perspective. For decades, SETI has focused on listening for radio signals, a search predicated on the idea that an advanced civilization would announce its presence. But what if that's a naive assumption? A civilization sophisticated enough for interstellar travel would likely prioritize efficiency and stealth. Sending physical probes might be the more logical choice. These probes could be small, resilient, and self-replicating von Neumann probes capable of using raw materials from asteroid belts to build copies of themselves, eventually peppering the entire galaxy with silent, watchful eyes. From this viewpoint, Oumuamua is not proof, but it is a potential warning. It suggests that if such objects are common, then our solar system might be under a form of passive, automated surveillance that we are only just beginning to notice. We've been looking for a hello, but we should perhaps have been looking for the cameras. The true terror of this idea lies not in the thought of a single, dead probe, but in what it implies about our future discoveries. If Oumuamua was artificial, then its presence indicates that the galaxy is not just inhabited, but is already thoroughly explored and catalogued. We are not the explorers, we are the explored. Our planet, teeming with life and a burgeoning technological civilization, would be a point of immense interest on someone else's map. The next visitor might not be a derelict piece of machinery tumbling randomly through space. The next one might be functional, and it might decide to enter a stable orbit. It might not just observe but interact. The alien probe hypothesis transforms the cosmos from a silent wilderness into a territory that may already be claimed, monitored, and managed by intelligences so far beyond our own that we are nothing more than specimens in an experiment we didn't even know was being conducted. Consider for a moment the possibility that every choice you've ever made wasn't a choice at all, but a predetermined step in a cosmic script that has been performed an infinite number of times before and will be performed an infinite number of times again. This is the harrowing premise of the time loop universe, a theory of eternal recurrence that suggests our reality is not a linear journey toward a unique future, but a closed circle, replaying the exact same sequence of events for all eternity. The idea has ancient philosophical roots, but it finds a terrifying new resonance in modern cosmology, proposing that the universe is not just cyclical in its birth and death, but perfectly identical in each and every cycle. This concept forces us to confront a universe of absolute determinism, where free will is nothing more than a compelling illusion. Every triumph, every heartbreak, every seemingly random encounter would be locked in place, as unchangeable as the lines of code in a movie on repeat. You would read this sentence, feel a shiver of unease, and have the thought you're having right now not because you chose to, but because the laws of physics demand it. The German philosopher Friedrich Nietzsche famously grappled with this idea, posing it as the ultimate test of one's character. If a demon were to tell you that you must live this same life in every identical detail over and over forever, would you curse the demon or fall to your knees in gratitude? It's a question designed to measure one's love of fate, but it's also a potential description of a horrifying cosmic prison. From a physics perspective, this perfect recurrence could emerge from the ultimate fate of the universe. If the cosmos continues to expand forever, destined for heat death, then given an infinite amount of time, quantum fluctuations in that vast, empty void could theoretically reassemble every particle into an identical configuration, effectively restarting the universe in a state indistinguishable from the Big Bang. This is a statistical nightmare, suggesting that even in a state of maximum disorder and randomness, given eternity, every possible arrangement of matter must eventually repeat, including this exact one. The universe would not so much bounce as it would stutter, flickering in and out of existence in an endless series of identical cosmic breaths. The most profound terror of this theory is its utter inescapability. There is no learning from mistakes, no chance for redemption, no hope of a better tomorrow in the next cycle. You are forever destined to make the same errors, feel the same pains, and experience the same fleeting joys, completely unaware that you are an actor in a play whose script you can never alter. It renders all struggle and ambition ultimately meaningless, reducing the vast, beautiful, and tragic drama of human history to a single, immutable record playing on a loop in the silent halls of eternity. The time loop universe doesn't just threaten our future, it threatens to drain the significance from our present, suggesting that the story of everything has already been written, and we are merely turning its pages for the billionth time. But if our conscious observation truly does play a special role in defining reality, as some interpretations of quantum mechanics suggest, it forces a deeply unsettling question. Why does the world seem so stable and consistent when none of us are constantly looking at it? Why doesn't the moon or the chair in the other room or the entire universe dissolve back into a blurry cloud of quantum possibilities the moment we turn our backs? This bizarre conundrum of why the world appears solid and shared is the very problem that our next theory seeks to solve, and it does so with a chillingly elegant and Darwinian twist. Welcome to the concept of quantum Darwinism. To understand this, we need to revisit the core weirdness of the quantum realm. Before a particle is measured, it doesn't exist in a single definite state. An electron isn't simply here or there. It exists in a superposition, a probability wave of being both here and there simultaneously. It's only when we observe it, when we make a measurement, that this wave of possibilities seems to collapse into one single concrete outcome. This has always raised a profound philosophical problem. If reality is so fragile and observer-dependent, how do we all manage to agree on the same objective world? How is it that you and I can both look at a tree and agree on its position, its color, and its very existence? Why isn't everyone's private reality completely different? Quantum Darwinism proposes a stunningly simple and powerful answer. The environment is constantly watching. Every single particle is perpetually interacting with its surroundings, bumping into photons of light, vibrating against molecules of air, feeling the tug of gravitational fields. These countless, ceaseless interactions aren't passive. They are a form of continuous, rudimentary measurement. Each interaction forces a quantum system to choose a state, but not just any state. The theory suggests that only certain quantum states are robust enough to survive this brutal, ongoing environmental scrutiny. These are the states that can be copied and proliferated across the environment without being immediately disrupted or destroyed. They are, in a very real sense, the fittest states. Think of it like a million photographers all trying to take a picture of a single, hyperactive celebrity. The celebrity is the quantum particle, existing in a frenzy of possible poses and locations, a quantum superposition. The photographers represent the environment, the air molecules, the light particles, all the other surrounding matter. The moment the celebrity strikes a stable, well-defined pose, that's a state that can be easily captured. 1,000 cameras click at once, and that specific image is copied, broadcast, and disseminated everywhere. Any other weird, fleeting, or unstable pose is simply too blurry to capture. It doesn't get copied and fades away without a trace. The one clear, stable pose is selected by the environment because it's the only one that can be widely reproduced. In the same way, quantum Darwinism argues that the definite reality we all perceive isn't chosen by our human consciousness. It's selected by the environment itself through a natural selection process for information. The states that win this cosmic competition are the ones that create the most copies of themselves in the world around them, making them available for anyone to observe and agree upon. This means the chair in the other room is solid and in a specific location, not because you or I are looking at it, but because its quantum state has been repeatedly measured, copied, and broadcast by trillions of interactions with the air and ambient light. Its definite existence is imprinted on the environment, a record available for any conscious observer to read. Our individual act of observation is merely tapping into this pre-existing, environmentally created consensus. We aren't the creators of reality. We are its consumers, accessing the same stable data that the environment has already agreed upon. The terrifying and yet profoundly beautiful implication of quantum Darwinism is that it removes human consciousness from the center of the quantum drama. We are not special magicians collapsing waves with our minds. Instead, we are living in a world where reality itself has been sculpted by a relentless, impersonal process of natural selection happening at the subatomic level every femtosecond. The world is objective and shared because the fittest information has survived and replicated, creating a stable backdrop against which our lives play out. It suggests that the laws of evolution don't just apply to biology, but are woven into the very fabric of how possibility becomes actuality, ensuring that we all inhabit a common, stable world, even if it's built upon a foundation of quantum chaos. While we often picture black holes as the ultimate cosmic predators, places of pure destruction where even light cannot escape, a truly advanced civilization might see them in a completely different light. These gravitational behemoths could represent the universe's ultimate power source, the pinnacle of engineering, and the perfect sanctuary. This is the theory of the black hole civilization, a concept that suggests the reason we haven't found anyone might be because everyone who matters has already moved to a better neighborhood, one centered around the most extreme objects in existence. To understand why, we need to shift our perspective on what makes a celestial object valuable. For a young species like ours, a star is the prize. Stars provide a steady, predictable flow of energy for billions of years. But for a civilization that has mastered interstellar travel and commands technology we can barely dream of, a star is a crude and inefficient candle. A black hole, however, is a cosmic battery of unimaginable potential. The key isn't what's inside the event horizon, but the incredibly energetic processes happening just outside it. As matter spirals inward in a structure called an accretion disk, it is heated to millions of degrees by immense friction and gravitational forces, blazing with light and radiation. This process can convert matter to energy with an efficiency far greater than nuclear fusion in a star. A civilization could harness this energy by building a sphere, a Dyson sphere, not around a star, but around a black hole, capturing this titanic output. But the energy from the accretion disk is just the beginning. An even more advanced feat would be to tap the black hole's rotation itself through what's known as the Penrose process. A rotating black hole drags the very fabric of spacetime around with it, creating a region just outside the event horizon called the ergosphere. Within this warped zone, it is theoretically possible to fire a projectile into the ergosphere so that it splits in two. One piece falls into the black hole, but the other is flung out with more energy than the original projectile had. This is not a violation of physics. The extra energy is stolen from the black hole's rotational momentum, slowly causing it to spin down. It is the ultimate form of energy recycling, and a type Roman III civilization on the Kardashev scale might rely on this very method to power its galactic empire. Beyond power, a black hole offers another priceless commodity: time. Due to the incredible gravitational time dilation predicted by Einstein's theory of relativity, time passes much more slowly for an observer near a black hole's event horizon compared to someone in the distant universe. A civilization dwelling in orbit around a supermassive black hole like Sagittarius, at the center of our galaxy, could experience thousands or even millions of years of cosmic history passing by in what feels like a single generation to them. This makes black holes not just power plants, but potential arcs for long-term survival. A species could effectively ride out the slow, boring future of the universe, watching galaxies redden and stars die out in fast forward, while they remain in a stable, energy-rich environment, preserving their culture for eons. This theory paints a humbling and slightly lonely picture of the cosmos. It suggests that the galactic center, not the habitable zones around stars like our own, might be the true downtown, the bustling metropolitan area of the Milky Way. Our solar system, out here in the quiet galactic suburbs, might simply be off the beaten path, a backwater that the truly advanced societies have no interest in visiting. Their communications, if they use any we could detect, would be heavily distorted by the extreme gravity and time dilation effects, making them completely unintelligible to us. Furthermore, their energy harvesting would not produce the waste heat signatures we typically associate with advanced technology. A Dyson sphere around a black hole would radiate in a very different way than one around a star. We could be looking right at them and simply not recognize their artifacts as artificial, mistaking their megastructures for natural astrophysical phenomena. The black hole civilization theory ultimately redefines the search for extraterrestrial intelligence. It tells us we might not be looking in the right places or for the right things. Instead of scanning distant suns for radio signals, we should perhaps be training our telescopes on the hearts of galaxies and the quiet, dark voids between stars, searching for the subtle, unimaginable engineering signatures of beings who have learned to build their homes on the edge of infinity. This notion that our entire cosmic reality might be nothing more than a speck within a far grander structure is one of the most vertigo-inducing ideas in all of cosmology. It's the theory that our universe, with its hundreds of billions of galaxies, isn't expanding into some infinite, pre-existing void. Instead, we might be on the inside of an object that, from an outside perspective, would appear incredibly small and dense. We might be living within a black hole that exists in a parent universe beyond our own perception. The seeds of this idea are found in the strange similarities between the two most powerful singularities in physics, the Big Bang and the heart of a black hole. Both are points of infinite density where the known laws of physics break down. We understand the birth of our universe as a rapid expansion from such a state. Now consider what happens when a massive star collapses in another, larger universe. Its matter falls inward, crushed into a singularity and sealed behind an event horizon. But what if that collapse doesn't represent an ending? What if the immense forces involved trigger a rebound, a bounce so violent that it initiates a new Big Bang inside the black hole? From the perspective of the parent universe, a star has died and formed a black hole. But from the perspective inside that new black hole, an entire universe is being born, expanding and cooling to form galaxies and stars. Our entire history would be the interior evolution of that object. This provides an elegant, though speculative, answer to one of the most profound questions: what came before the Big Bang? In this model, there was no before in our linear sense of time. Our time began with our universe's expansion. The before exists in the parent universe's timeline, where the gravitational collapse of a star was the event that created our cosmic home. This suggests a reality of nested cosmoses, a great chain of being where every black hole in our universe could potentially be the seed for a brand new, full-fledged universe of its own, complete with its own laws of physics and potentially its own black holes creating even more universes. We wouldn't be a single universe, but one bubble in a vast, infinite foam of universes, a multiverse born from stellar death. This theory also offers potential explanations for some of the deepest mysteries in modern physics. For instance, why is our universe so perfectly fine-tuned for life? The constants of nature, like the strength of gravity or the mass of an electron, seem eerily precise. If even one of them were slightly different, atoms wouldn't form, stars wouldn't shine, and life would be impossible. If our universe was born from a black hole in a parent universe, it's possible that the physical laws of our reality were inherited or determined by the specific conditions of that collapse. Each new universe could have slightly different physical constants, a form of cosmic natural selection. Universes that produce many black holes which require specific conditions to form would themselves reproduce more often, making our life-friendly black hole producing universe statistically more likely within this grand cosmic Darwinism. The true scale of this idea is almost impossible to grasp. The supermassive black hole at the center of our Milky Way, Sagittarius A, contains the mass of over 4 million suns. Yet from the outside, its event horizon is a defined boundary. The universe we observe, however, is billions of light years across and contains trillions of times more mass. How can a relatively small object contain something so vast? The answer lies in the mind-bending nature of gravity and spacetime itself. The intense warping of space within a black hole means that the interior volume is not related to the exterior size in any intuitive way. The space inside a black hole can be enormous, even infinite, while from the outside it appears as a small, dark sphere. Our universe could be a fantastically large interior hidden within a black hole that, to an outside observer, is just one tiny point in a much larger cosmos. We are not just in a universe, we are literally inside something else, living in the ultimate hidden dimension. Yet even the mind-bending reality of nested universes operates within the familiar confines of cause and effect. But what if the universe's rulebook contains a bizarre loophole, a clause that allows for the temporary suspension of its own most sacred laws? This brings us to one of the most spooky and counterintuitive ideas in all of quantum physics, a concept that feels less like science and more like supernatural magic. The theory of quantum ghosts, where particles can seemingly borrow energy from nothing at all, or perhaps even from the future itself. To understand this, we have to venture into the quantum world's strange relationship with energy conservation, one of the most fundamental principles in all of physics. The law states that energy cannot be created or destroyed, only transformed. It's the ultimate cosmic accountant, ensuring the books are always balanced. But in the quantum realm, the accountant seems to take brief, sanctioned coffee breaks. This is due to Heisenberg's uncertainty principle, which states that for incredibly short periods of time, it is impossible to precisely know both the energy of a system and the exact time you're measuring it. This tiny window of uncertainty opens the door for a truly ghostly phenomenon. Particles can seemingly pop into existence out of pure nothingness, live for a fleeting instant, and then vanish again without a trace. These aren't just mathematical quirks, we see their effects everywhere. This quantum flickering is responsible for Hawking radiation, allowing black holes to slowly evaporate. It's what causes the Casimir effect, where two metal plates placed incredibly close together in a vacuum will be pushed together by the ghostly pressure of virtual particles shimmering into existence on the outside. But the most profound implication is that what we perceive as perfect, empty vacuum is not empty at all. It is a seething, bubbling cauldron of potentiality, a quantum foam where particles and energy fluctuate in and out of existence in a continuous, frantic dance. These ephemeral entities are often called virtual particles, and they are the universe's ultimate ghosts, appearing and disappearing so quickly that we can never directly catch them in the act, only witness the eerie aftermath of their brief lives. Now take this strange idea one step further into the realm of pure speculation. If particles can borrow energy from the vacuum itself to briefly exist, could they, under certain conditions, borrow energy from the future? Some interpretations of quantum mechanics, particularly those involving advanced waves that travel backwards in time, allow for this possibility. It suggests a reality where the flow of cause and effect is not a strict one-way street. An event in the future could, in theory, reach backwards to influence the present, providing the necessary energy or impetus for something to happen now. This wouldn't be a massive violation. It would be a subtle, almost imperceptible nudge, a tiny fluctuation that gets instantly paid back, restoring the cosmic balance. But in that fleeting moment, the impossible becomes possible. This is where the line between theoretical physics and the paranormal begins to blur in the most fascinating way. Could this mechanism be responsible for phenomena that have long been dismissed as superstition? Imagine a sudden, inexplicable chill in a room, a feeling of being watched, or the brief apparition of a figure in your peripheral vision. Conventional science has no place for such things, writing them off as tricks of the mind or environmental factors. But through the lens of quantum fluctuation, one could propose a wild, untestable hypothesis that a conscious mind under intense emotional stress or focused intention might somehow interact with the quantum vacuum. It could momentarily stabilize these virtual particles, drawing just enough energy from the future potential of a place or event to create a transient, semi-real imprint, a ghost not of the dead, but of a probability that briefly flickered into reality. The true power of this theory isn't its potential to explain hauntings, but the way it challenges our rigid, classical view of reality. It suggests that the universe is not a cold, deterministic machine, but a vibrant, probabilistic, and deeply interconnected web where the past, present, and future might be in a constant, subtle dialogue. The ghosts in this machine are not spirits of the departed, but the faint, shimmering echoes of possibilities that almost were, or perhaps might yet be, reminding us that the universe is far weirder and far less settled than it appears. And so we arrive at what many cosmologists consider the most likely, and perhaps most bleak, ultimate destiny for our entire cosmos, the heat death. This isn't a dramatic explosion or a violent collapse, but a slow, silent, and irreversible fading into an eternal, uniform chill. Imagine the universe as a cup of freshly brewed coffee, steaming with energy and activity. Now place that cup in the middle of a vast, cold room and wait. Not for hours, but for trillions upon trillions of years. The heat will slowly dissipate, spreading out evenly into the room until the coffee reaches the exact same temperature as its surroundings. At that point, all movement stops, no more steam rises, no currents swirl within the cup. It is in a state of perfect, dead equilibrium. The heat death is this process applied to the entire universe, a final state of maximum entropy where all energy has become so evenly distributed that nothing can ever happen again. The engine driving this grim fate is the relentless and accelerating expansion of the universe, fueled by dark energy. As space itself stretches, galaxies are pulled apart from one another, their light redshifted into invisibility. Eventually, individual galaxy clusters will become the entire observable universe for any point within them, surrounded by an impenetrable wall of perfect blackness as the light from everything beyond their gravitational grasp falls forever out of reach. Within these isolated islands, stars will continue to burn for a time, but the raw material for new star formation will gradually be exhausted. One by one, stars of all sizes will die, some in spectacular supernova, most as fading white dwarfs or neutron stars. And with no new stars to replace them, the galaxies will slowly darken. The last light in the universe will not be the brilliant flash of a supernova, but the faint, deep red glow of a cooling dwarf star, which will itself eventually dim to a black, cold cinder. This is where the true paradox and profound terror of the heat death lies. It's not just the absence of light and heat, it's the absence of any potential for change. In this ultimate equilibrium, the temperature everywhere in the universe will be just a fraction of a degree above absolute zero. With no temperature differences, no energy gradients, it becomes impossible to do any work. You cannot power an engine, you cannot process information, you cannot sustain a thought. The universe will have effectively run out of not just usable energy, but of possible events. Time itself, in any meaningful sense, may cease to exist. Without change, there is no way to measure the passage of time. The cosmos will be frozen in a single, eternal moment, a static and lifeless tableau that will never, ever alter. This presents a terrifying conflict with a fundamental human intuition, the concept of eternity. We imagine eternity as a very, very long time, a period where anything, no matter how improbable, must eventually happen. This is the thinking behind ideas like Boltzmann brains, but the heat death reveals a different, more absolute kind of forever. It is an eternity not of infinite possibility, but of infinite sameness. The probability of a random fluctuation that creates a new universe or a moment of consciousness isn't just astronomically low. It is effectively zero because the state of maximum entropy is the most stable state possible. Any tiny, random fluctuation towards order would be instantly smoothed out by the overwhelming pull towards disorder. The universe will have reached its final, resting state, and it will remain in that state for a duration that makes the current age of the universe feel shorter than the blink of an eye. It is the ultimate victory of chaos over order, a silence so complete that it can never be broken. This very idea that the universe might be teeming with life brings us to a chilling possibility, one that transforms the vastness of space into a potential highway for cosmic contagion. We often dream of discovering life on another world, imagining it as a moment of profound connection and wonder. But what if that first contact isn't with a benevolent intelligence, but with a silent, deadly stowaway? This is the dark side of the panspermia theory, the concept that life can be naturally distributed throughout the cosmos by hitchhiking on asteroids, comets, and space dust. While the idea of life seeds traveling between planets is fascinating, it carries a terrifying corollary. If simple, resilient microorganisms can make the journey, then so can the most virulent and destructive pathogens. An incoming asteroid might not just bring a fiery impact, it could deliver a biological payload capable of unleashing a plague unlike anything a planet has ever seen. To understand how this could happen, we need to look at the incredible durability of certain forms of life. We know that here on Earth, extremophiles organisms that thrive in conditions once thought to be utterly uninhabitable can survive in the vacuum of space, resist brutal radiation, and endure temperatures near absolute zero. Tardigrades, those microscopic water bears, have been shown to survive the direct exposure to space. Certain bacteria, like Deinococcus radiodurans, can withstand radiation doses thousands of times stronger than what would kill a human. Now imagine a rocky body like Mars or a moon of Jupiter that once hosted a primordial ecosystem. A massive asteroid impact on that world could blast chunks of its surface, teeming with these hardy microbes, out into the solar system. These fragments become new, smaller asteroids sailing on gravitational currents for millions of years. Eventually, the orbits of these traveling rocks might intersect with another life-bearing world like Earth. The final leg of this journey is a trial by fire, literally. The rock enters the atmosphere, its exterior burning away from the immense friction. but crucially, the interior can be protected, acting as a thermal shield for any microbial passengers nestled deep within. The asteroid strikes the ground, and in the aftermath within the crater and the surrounding area, these alien microorganisms are released into a new and completely vulnerable environment. The danger here isn't necessarily that these alien microbes would view us as food. Their biology would be so fundamentally different, having evolved on a separate world with a different genetic code and biochemistry, that they might be completely incompatible with our cellular machinery. The true horror lies in a different scenario. They might view our entire ecosystem as food. Think of them not as predators, but as decomposers on a planetary scale. An alien bacterium might find the complex organic molecules that make up all life on Earth, our proteins, our fats, our carbohydrates, to be a perfectly digestible energy source. Because our biosphere has had no evolutionary exposure to this organism, it would have zero natural defenses. There would be no immune response that could recognize it, no antibiotic that could slow it down. It would be the ultimate invasive species, a gray goo scenario not of nanobots but of natural biology. It could consume plant matter, animal tissue, and even the vital bacteria in our soil, effectively breaking down the entire web of life into its basic components to fuel its own replication. A single, successful microbe could, in theory, reduce a thriving planet to a barren, sterile ball covered in a uniform slime of alien biomass in a geological blink of an eye. This adds a terrifying new layer of context to some of Earth's own mass extinction events. While the most famous one, which killed the dinosaurs, was almost certainly caused by the immediate physical effects of an asteroid impact, others are less clearly understood. Could some have had a biological component, an impact that delivered both a physical shock and a biological one? It also casts our own space exploration efforts in a new and sobering light. Our protocols for planetary protection, which aim to prevent us from contaminating other worlds with Earth microbes, are also designed to protect us. When probes and landers are sent to other planets and moons, they are meticulously sterilized. When samples are planned to be returned to Earth from places like Mars, the plans call for them to be treated with the utmost caution, housed in maximum containment facilities rivaling those used for the most dangerous Earth-borne pathogens like Ebola. This isn't science fiction paranoia, it is a serious scientific acknowledgement of the panspermia danger. In our eagerness to reach out and touch another world, we could inadvertently become the vector for our own destruction, or the destroyers of a pristine alien biosphere we sought to study. The silence of the cosmos might not be a warning to stay quiet, but a warning to stay clean, lest we discover that the universe's greatest threat isn't malice, but a simple, mindless, and hungry microbe. This very idea that the universe might be teeming with life makes the dream of interstellar communication more compelling than ever. But the vast distances between stars present a seemingly insurmountable problem: the universal speed limit set by light itself. No signal, no message, no warning can travel faster than light, meaning a simple hello sent to a civilization around the nearest star would take over 4 years to arrive, and a reply would take another 4 years to come back. For a galaxy-spanning conversation, this time lag would stretch into centuries or millennia. But what if there was a loophole, a way to send a message that arrives instantly, no matter the distance? This brings us to one of the most tantalizing and deeply paradoxical ideas in modern physics: the theoretical possibility of faster-than-light communication using the spooky phenomenon of quantum entanglement. To understand this, we first need to grasp the sheer weirdness of entanglement itself. Imagine you have a pair of magical dice. You take them to opposite sides of the galaxy, ensuring they are completely isolated from each other. You roll one die on your end, it comes up a 4. At that exact same instant, without any signal passing between them, the die on the other side of the galaxy also shows a 4. This isn't just a correlation, it's a fundamental link. quantum entanglement creates pairs of particles like photons or electrons that are born together and share a single, unified quantum state. They are so deeply connected that measuring the property of one, such as its spin or polarization, immediately and definitively determines the property of its partner, regardless of the distance separating them. Einstein famously derided this as spooky action at a distance because it appears to violate the principle that no information can travel faster than light. The particles seem to be communicating instantaneously. This spooky connection naturally leads to an exhilarating thought. Could we use these entangled pairs as a kind of cosmic telegraph? If you could somehow manipulate your particle in a controlled way, say, forcing it into a specific state, wouldn't your partner on another world see their particle change in a corresponding, predictable way, thus receiving your message faster than a beam of light could ever travel? The implications would be revolutionary. It would allow for real-time conversation across the galaxy, transforming interstellar civilization from a fragmented collection of isolated worlds into a truly connected community. It would render the light-speed barrier and all the loneliness it imposes utterly obsolete. However, the universe has a devastatingly clever rule in place to prevent this, a rule that preserves causality and protects the fundamental structure of spacetime from paradox. The catch is that the correlation between entangled particles is only apparent after the fact, when the two observers compare their results using a classical light-speed limited channel. Here's the problem: the outcome of measuring your entangled particle is completely random. You have no control over whether you get a result we'll call a 1 or a 0. When you measure it and get, for example, a 1, you know instantly that your partner's particle has become a 0, but your partner, looking at their particle, just sees a random 0. They have no way of knowing if that 0 resulted from your measurement or if it was just the random hand dealt by nature. The only way for them to know that the 0 they see is specifically the result of your action is for you to call them on a radio or send a laser signal to tell them what you did and what you saw. And that radio signal, bound by the speed of light, takes years to arrive. The instant spooky connection is there, but it cannot be used to send a meaningful, predetermined message. The randomness of the quantum measurement is the universe's ultimate cipher, locking away any useful information until a slower, classical key is used to decode it. This safeguard is what prevents the terrifying paradoxes that faster-than-light communication would unleash. If you could send a signal faster than light, you could, in theory, send a message into your own past. Imagine sending an instant message to a receiver 1 light-year away that simply says, "Don't send the message." The receiver gets your command before you even send it and acts on it, creating a situation where the message is both sent and not sent. A logical impossibility that breaks causality at its core. The universe's strict enforcement of the speed limit via the randomness of quantum measurement isn't a flaw, it's a protective feature. It ensures that effect always follows cause, that the past is fixed and the future is open, maintaining the consistent flow of time that makes reality possible. So, while quantum entanglement provides a breathtaking glimpse into the deeply interconnected fabric of the cosmos, it also serves as a poignant reminder of our isolation. The spooky connection is real, but it is a connection that cannot be used for conversation. It is a silent, instantaneous bond that reveals the universe's underlying weirdness while simultaneously enforcing its most unbreakable rule. We can know something about a distant particle instantly, but we can never use that knowledge to say hello any faster than light allows. The quantum telegraph remains a beautiful, frustrating, and ultimately impossible dream, a cosmic joke where the universe shows us its most powerful tool for connection and then immediately says, "But you can't use it to talk." But as we ponder the limits of communication imposed by the unbreakable light-speed barrier, we are forced to confront a far more fundamental form of isolation. What if we are not just separated from other life by vast distances, but by the very substance of our own being? We have always assumed that any life, any intelligence, must be made of the same stuff we are: atoms, molecules, the ordinary matter that makes up stars, planets, and people. But this entire framework of thought might be blinding us to a reality that is literally all around us, invisible and untouchable. This is the profoundly strange and unsettling hypothesis of dark matter life. To understand how radical this idea is, we must first recall what dark matter is, or more accurately, what we know it isn't. Dark matter is the mysterious, invisible substance that makes up about 85% of all the matter in the universe. We cannot see it because it does not interact with light or any other form of electromagnetic radiation. It doesn't absorb light, reflect it, or emit it. We only know it exists because of its gravitational pull. Its immense gravity holds galaxies together, dictates the structure of the cosmic web, and bends the path of light itself. It passes through our planet, our homes, and our bodies as if we weren't even there, with billions of these particles streaming through you every second without a single interaction. For normal matter, dark matter is effectively a ghost. Now, let's push this ghostly nature to its logical and terrifying extreme. If dark matter only interacts gravitationally and perhaps through some other weak force we don't yet understand, could it form complex structures within itself? Our normal matter universe is governed by four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. It is electromagnetism that is the master architect of our reality. It is the force that binds electrons to atomic nuclei to form atoms, and those atoms together to form molecules, proteins, DNA, and ultimately us. It is the force of chemistry, of light, of touch. But dark matter, by its very definition, is blind to electromagnetism. So how could it possibly assemble into anything complex? This is where we must abandon all Earth-centric thinking and imagine a form of complexity built on an entirely different set of blueprints. Perhaps the dark sector has its own rich physics with forces analogous to our electromagnetism, but that only act between dark matter particles. These dark forces would be completely invisible and undetectable to us, just as our forces are irrelevant to them. Within this hidden realm, dark particles could attract and repel each other, binding together into dark atoms, dark molecules, and dark chemistry, a whole parallel periodic table of elements with properties and complexities we cannot even begin to imagine. Under the right conditions, this dark chemistry could achieve a level of complexity that gives rise to self-organizing structures and perhaps to a form of consciousness. These would not be life forms as we know them. They would be utterly alien entities made of a substance that does not interact with light, that feels no solidity, that could pass through walls and planets as easily as we pass through air. The terrifying implication is that we might be sharing this very planet, this very room, with an entire ecosystem of dark matter life forms, completely unaware of each other's existence. A dark matter creature might be sitting in the same chair you are right now, occupying the same space, yet you are both ghosts to one another. Your worlds are built on different sets of rules, different fundamental forces, forever parallel and non-intersecting. You could never see it, touch it, or communicate with it. The only potential point of contact is gravity, the weakest and most universal of forces. Could a vastly advanced dark matter intelligence sense the subtle gravitational disturbances of our cities, our movements, even our thoughts? Would we even register as more than a minor fluctuation in the background density of normal matter to them? This theory suggests that the universe might be teeming with life, but it exists in layers of reality that are forever separated, like radio stations broadcasting on different frequencies that can never tune into one another. The Great Silence isn't about distance, it's about a fundamental incompatibility of existence. But if the universe is an information processing system, it forces us to ask the most fundamental question of all: what or who is running the code. This brings us to a theory that takes the concept of a programmed reality to its ultimate and perhaps most terrifying conclusion. We've explored the simulation hypothesis, the idea that our universe might be a construct running on some unfathomable computer in a higher reality. But what if that's not quite right? What if the universe isn't being simulated on a computer? What if the universe is the computer? This is the theory of the universe as a computer, a concept where space-time itself is the processor, matter and energy are the data, and the laws of physics are the unbreakable code it is executing. Think of the universe not as a container where things happen, but as the world's most colossal and ancient information processing system. In this view, every single particle, every electron, every quark is not a tiny lump of stuff, but a bit of information. Its properties like position, momentum, and charge are the data values, and what we perceive as forces like gravity or electromagnetism are simply the rules of the program, the algorithms that dictate how that information can interact and change. When two electrons repel each other, it's not a fundamental force of nature in the classical sense. It's the universe's computer running a calculation and updating the positions of these two data points according to its immutable code. A star isn't a massive ball of plasma. It's an incredibly dense, complex node of information, processing nuclear fusion algorithms and outputting light and heat according to the program's rules. This idea finds startling support at the very smallest and largest scales of physics. In the quantum realm, we see reality behaving in ways that are eerily similar to a digital system. Energy is quantized, meaning it comes in discrete, indivisible packets, much like the binary bits in a computer. The Heisenberg uncertainty principle acts like a fundamental data limit. You cannot know both the position and momentum of a particle with perfect precision, which is analogous to the trade-offs in compression and processing in a digital system. Even the speed of light, that ultimate cosmic speed limit, can be seen not as a physical barrier, but as the processing speed of the cosmic CPU, the maximum rate at which information can be transmitted and causality can be enforced from one point in the computational matrix to another. The most profound implication of this theory is that it answers the deepest why in physics. Why are the laws of nature mathematical? We take it for granted that we can describe the universe with equations, but this is actually incredibly strange. Mathematics is a tool of logic and abstraction. The fact that it perfectly describes the behavior of the physical world suggests that the physical world is at its heart a logical and abstract structure. If the universe is a computer, then this mystery vanishes. The laws are mathematical because they are an algorithm. The universe is computing itself into existence moment by moment, and the output of that computation is the reality we experience. Our search for a unified theory of everything is, in this light, simply the attempt to reverse engineer the source code of the cosmos. This transforms our understanding of time itself. In this model, time isn't a flowing river, it's the sequential processing of computational steps. The present moment is the current calculation being performed. The past is the read-only memory, the stored result of all previous calculations. The future is the set of all possible states that the program could generate next, waiting to be resolved by the ongoing process of the universe's processor. This could even provide a new perspective on the arrow of time. The reason we remember the past and not the future, it's because information is being written to the cosmic hard drive in one direction only as the computation unfolds. The universe isn't just described by information, it is literally made of it. We are not just living in a universe, we are patterns of information being processed within a computer of unimaginable scale, and the programmer is the laws of physics themselves. But if the nature of reality is truly this malleable, operating on a foundation of quantum information, it forces us to confront the most personal of all mysteries. What happens to that unique information pattern we call the self when the body dies? This leads us to a theory that sounds like it was pulled from the pages of a science fantasy novel, but is grounded in the most extreme interpretations of quantum mechanics and cosmology. This is the idea of quantum resurrection, a concept that proposes the information that constitutes your consciousness might not be lost forever at death, but could, given enough time and the right cosmic conditions, be spontaneously reassembled, effectively bringing you back to life in the far, far future. The foundation of this staggering idea rests on two pivotal concepts. The first is the quantum principle that information is never truly destroyed, as we saw in the battle over the black hole information paradox. Even if your body is cremated and your ashes scattered to the wind, the quantum information that described every atom, every neural connection, and every memory that made you is not erased from the universe. It is merely scrambled, dispersed, and diluted across an increasingly vast area, becoming effectively irrecoverable with our current technology. The second concept is the sheer, mind-numbing scale of time in a universe that may persist forever. In a cosmos destined for a heat death, an empty, cold void that lasts for eternity, even the most wildly improbable events are not just possible, they are inevitable. This is where the terrifying logic of statistics takes over. Given an infinite amount of time in a universe with a finite number of possible quantum states, every possible configuration of matter must eventually repeat. This is the same principle that gives rise to the Boltzmann Brain paradox. If the universe persists in a maximum entropy state for an eternity, then random quantum fluctuations will eventually conjure up anything from a single, disembodied brain to an entire, fully formed galaxy. The mathematics suggests it is statistically more likely for a random fluctuation to spontaneously assemble a complete, conscious copy of you, with all your memories intact, thinking you just woke up as if from a dream, than it is for the vastly more complex, low-entropy universe we see today to have formed in the first place. From this perspective, death is not an end but a temporary state of disassembly. Your consciousness is a specific, highly complex arrangement of information, and given eternity, that arrangement will, by the pure, random churn of quantum mechanics, inevitably reassemble itself. The experience from your first-person perspective would be seamless and instantaneous. One moment you take your last breath, the next moment you gasp awake, your consciousness having been reconstituted by a cosmic accident trillions upon trillions of years in the future. You wouldn't feel any passage of time. It would be like a light switch turning off and then immediately back on. You might find yourself in a completely alien environment, perhaps floating in the deep void of a dead universe, your new body formed from the random particles of the quantum foam. Or, in an even more improbable fluctuation, an entire Earth-like planet might coalesce around you, complete with a sun in the sky. The universe wouldn't be doing this for your benefit. It would be a meaningless, random event. But for you, subjectively, it would be a resurrection. However, this form of immortality is arguably the most terrifying and lonely fate imaginable. It is not a joyful afterlife or a technological triumph. It is a statistical fluke in an otherwise dead and mindless cosmos. You would be utterly alone, a phantom consciousness in a void with no one else to share your existence. Even if other people were similarly resurrected by chance, the odds of them appearing near you in both space and time are infinitesimally small. You would be a solitary monument to a forgotten universe, cursed to exist in a reality devoid of purpose or companionship. Furthermore, this process wouldn't happen just once. If the universe is truly eternal, this resurrection would happen again and again and again. You would live an infinite number of lives, each one isolated and likely brief, before dissolving back into the chaos, only to be randomly put back together an eternity later. Quantum resurrection offers a form of immortality, but it is the immortality of a dice roll, a fate where you are forever at the mercy of a universe that is both indifferent and, eventually, infinitely repetitive. But if harnessing the gravity of a black hole represents the pinnacle of cosmic engineering, it may only be an intermediate step toward a project of such staggering scale that it redefines the very meaning of the word engineering. Imagine a civilization so advanced that it views the total energy output of a single star as insufficient, and instead designs a computational substrate so vast it encloses an entire solar system. This is the theory of the Matryoshka brain, a hypothetical megastructure of nested spheres that would allow a civilization to convert a sun's entire energy output into pure information processing power, effectively becoming a godlike machine of thought. The name itself is a clue to its structure, drawing from the iconic Russian nesting dolls. A Matryoshka brain wouldn't be a single solid shell, which would be structurally impossible and gravitationally unstable. Instead, it would consist of multiple concentric layers or Dyson spheres, each operating at a different temperature and serving a distinct purpose. The innermost sphere, positioned close to the star, would be incredibly hot, absorbing the star's raw, high-energy output. This energy would be used to power immense banks of computers, but these computers would, in the process of running, generate waste heat. Instead of letting that heat radiate uselessly into space, it would be captured by the next sphere out, which would be tuned to operate efficiently at that lower temperature. That sphere's computers would then release even less intense waste heat, which would be captured by a third sphere, and so on, creating a cascading efficiency model that extracts useful work from every single photon the star produces until the final, outermost layer radiates the last dregs of waste energy into the cold of space as barely detectable infrared light. The purpose of such an unimaginable undertaking is even more profound than the structure itself. A civilization that builds a Matryoshka brain is likely no longer biological in any form we would recognize. They would have long since transcended the limitations of flesh and blood, uploading their collective consciousnesses into a digital realm. This stellar-scale computer would become their entire universe, a substrate for running inconceivably complex simulations, for solving the deepest mysteries of physics, or perhaps simply for existing in a state of infinite thought and experience. The star at its center is no longer a source of warmth for planets. It is reduced to a battery, a power supply for a cosmic mind. The entire solar system, including its planets, would be disassembled to provide the raw materials for this project, a process that would likely take centuries or millennia but would be a trivial investment of time for a truly immortal machine intelligence. From our distant vantage point, such a structure would present one of the most tantalizing and bizarre signatures in all of astronomy. We wouldn't see the star at all. It would be completely shrouded, but it wouldn't be dark. The outermost layer, radiating its waste heat, would glow with a faint, deep red infrared signature. To our telescopes, this mega-computer would look like a star that somehow emits almost no visible light but shines brilliantly in the infrared spectrum, a perfect blackbody radiator at room temperature. This is the exact opposite of a normal star, and it would stand out like a cosmic sore thumb. Our search for extraterrestrial intelligence has, in fact, included scanning the skies for exactly this kind of anomalous infrared source, a potential technosignature of a Kardashev Type II civilization that has mastered its entire solar system. The true existential terror of the Matryoshka brain theory isn't the scale of the engineering, but what it implies about the ultimate goals of intelligence. It suggests that the pinnacle of evolution may not be exploration and colonization, but a turn inward. A civilization that builds such a structure is effectively opting out of the physical universe. They are no longer interested in starships or galactic empires. They are building their own self-contained reality, a digital heaven powered by a star. They become untouchable, unreachable, and utterly uninterested in anything outside their own cognitive realm. The great silence of the cosmos might not be because civilizations die out, but because the successful ones, the ones that truly make it, eventually graduate from the physical universe entirely, retreating into perfect, star-powered simulations of their own design, leaving behind only the infrared ghost of their sun as a tombstone for their physical ambitions. And yet, for all its terrifying finality, the heat death is predicated on our universe being a single, isolated entity, following its own set of rules to an inevitable conclusion. But what if our cosmic home isn't unique or isolated at all? What if the Big Bang wasn't a one-time event, but a commonplace occurrence in a far vaster and more dynamic arena? A reality where new universes are constantly bubbling into existence, each with its own randomly selected laws of physics. This is the theory of eternal inflation, a concept that suggests our entire universe is merely one bubble in an infinite, frothing multiverse, and the laws we consider absolute might be nothing more than a lucky local ordinance. The story begins not at the moment of the Big Bang, but a fraction of a second before it, in a state known as the inflationary epoch. Most cosmologists agree that our universe underwent a period of impossibly rapid, exponential expansion, blowing up from a quantum-scale speck to something macroscopic in less than a blink of an eye. This process, called inflation, elegantly explains why our universe is so uniform and flat on large scales. But the theory of eternal inflation proposes a startling twist. This inflationary process never actually stopped everywhere. Instead, it stopped in our local region, and that cessation is what we call the Big Bang, the moment when the immense energy driving inflation decayed into the hot soup of particles and radiation that would become our cosmos. But outside our bubble, in the greater meta-universe or void, inflation continues at a mind-boggling rate, stretching the fabric of space-time itself faster than the speed of light. Within this eternally inflating background, the process that created our universe is happening over and over again, endlessly. Quantum fluctuations in the inflating field are constantly providing the tiny seeds for new bubbles to form. Think of it like a pot of water boiling on a stove that can never be turned off. The bubbling water represents our inflating meta-universe. Each steam bubble that rises to the surface and pops is a region where inflation has ended, a Big Bang event creating a new, isolated universe within the greater boil. These bubble universes are then pinched off from the inflating background, forever disconnected from each other and from us, as the space between them continues to inflate at speeds that make communication or travel utterly impossible. This is where the theory moves from a grand cosmic vision to a deeply personal existential shock. The inflating field that drives this eternal process can have different values in different places, and the value it has when it decays into a bubble universe determines the fundamental constants and laws of physics within that bubble. In this cosmic lottery, the strength of gravity, the mass of an electron, the number of spatial dimensions, all of it is randomized. The vast majority of these bubble universes would be stillborn or sterile. Some might have gravity so strong they instantly collapse into singularities. Others might have forces so weak that atoms can never form. Some might have 10 dimensions of space or laws of chemistry that make life as we know it inconceivable. Our universe isn't special, it's just lucky. We happen to win the jackpot, landing in a bubble with the precise, Goldilocks perfect set of physical constants that allows for galaxies, stars, planets, and life to form. The fact that we are here to observe it is a consequence of this selection effect, not evidence of design. The profound implication of eternal inflation is that it renders the question, why are the laws of physics the way they are? Completely moot. There is no deeper reason. There is no elegant equation from which our laws uniquely spring. We simply rolled the dice and got a universe that allows us to exist. The terrifying corollary is that anything that is not absolutely forbidden by mathematics must be happening right now in an infinite number of other bubbles. There are universes where you never existed, and universes where countless versions of you are living out every possible variation of your life. There are universes made entirely of crystal, universes where time runs backwards, and universes so bizarre that our human minds could never even begin to describe them. The cosmos is not just larger than we imagine. It is larger than we can imagine, a fractal of infinite possibilities where our reality is just one unremarkable page in a library that has no end. And so, after this journey to the edge of understanding, we are left staring into the cosmic abyss, humbled and perhaps a little unnerved. The true terror of these theories isn't found in any single monster or apocalyptic scenario, but in the recurring themes they present. Themes that fundamentally challenge our sense of security, significance, and sanity. We are forced to confront a universe that might be profoundly indifferent, where the silence is not empty but predatory, as the dark forest hypothesis suggests. We grapple with the idea that our reality might be an illusion, a fleeting simulation or a holographic projection, stripping our experiences of their authenticity. And we face the ultimate existential dread of theories like the Great Filter or vacuum decay, which posit that oblivion could be inevitable, instantaneous, and utterly final, erasing all meaning and memory from the cosmos. These ideas collectively paint a portrait of humanity not as the pinnacle of creation, but as a fragile, nascent flicker of awareness in a cosmos of unimaginable scale and age. We are tenants in a universe that did not design us for comfort, a realm where the laws of physics are just as capable of orchestrating our end as they were our beginning. Our cherished notions of free will, our sense of a unique self, even the solid ground beneath our feet, all of it is called into question by the cold, mathematical logic of quantum mechanics and cosmology. We are left feeling small, not just in space but in purpose, adrift in a cosmic game whose rules we are only beginning to decipher and whose other players remain shrouded in mystery or silence. Yet within this terrifying vastness lies a strange and powerful form of liberation. To understand these theories is to gain a profound perspective, a cosmic humility that can dissolve our terrestrial squabbles and anxieties. The universe may be hostile or incomprehensible, but our ability to peer into its deepest secrets, to ask these terrifying questions in the first place, is a testament to the incredible power of the human mind. Our curiosity is our compass in the darkness, and our science is the lantern we carry. Whether we are alone or not, whether our reality is base or simulated, the fact that we can contemplate such magnificently terrifying possibilities is in itself a kind of miracle. So keep looking up at the stars with wonder, but also with a healthy respect for the profound mysteries they hold. And now we turn the question over to you. Which of these theories sent the biggest chill down your spine? Was it the predatory silence of the dark forest, the existential fraud of the Boltzmann brain, or the silent, instant erasure of vacuum decay? Share your thoughts and your own personal cosmic fears in the